Hello students, so in the previous class we introduced series solution, and there we learned some terminologies, ordinary point, singular points, regular singular point, irregular singular point, and we also sort of learned the technique on how to solve, but only the theory part of it, right? So if you have ordinary point and if you need to find out the series solution, you simply put y is equals to summation n from 0 to infinity a n x to the power n, and you determine a n. In case if you have a singular point, then we have to be a little bit cautious, because then this expression will no longer work, because we can show very easily that if you take this expression, then all the an's will become 0, and that is why that will not be the ideal solution. So basically you are saying y is equals to 0 is the solution, which is not all the time true. So we have to come up with a different technique. So in today's class, I will take two examples, one for ordinary point, one for the singular point, and we'll see how to solve them. All right. So just two examples. Okay. So example one, solve the linear differential equation y double dash plus 3x into y dash plus 3y is equals to 0 near the ordinary point, x equals to 0, right? Solution. So since x equals to 0 is the ordinary point, let us take the solution. We can call this as equation 1. Let us take the solution of the form yx equals to summation n running from 0 to infinity a n x to the power n. Call it as equation number 2. So since we substitute this yx in equation 1, what we will get? So you have to calculate the first order and second order derivative. So we can write then from equation 1 and 2, what do we get? We will get summation n running from 0 to infinity n minus 1 a n x to the power n minus 2 plus 3 x summation n running from 0 to infinity n x to the power n minus 1 plus summation n running from 0 to infinity a n. Of course, there is a 3 and here also we will have a n x to the power n equals to 0. Hopefully, I did it correctly. So summation n running from 0 to infinity n minus 1 a n x to the power n minus 2 plus this can be further written as summation n running from 0 to infinity n minus 1 a n x to the power n minus 2 plus summation, what do we get? We will get n into n minus 1. So we have n into n minus 1 a n x to the power n minus 2 3x summation n from 0 to infinity n a n x to the power n minus 1 plus this. And what do we get? Basically, we will get summation n running from 0 to infinity. We'll have 3n plus 3 a n x to the power n, right. So we have d square y by dx square as n into n minus 1 a n x to the power n minus 1, and dy dx as n into x minus a n into x to the power n minus 1, and then we have 3y. So basically we are getting 3n plus 3 a n to the power x xn, right. And here we have x to the power n minus 2. So this is correct, right. Now we will we'll just play with the terms, right. So I'm little cautious when I'm doing these calculations, because a simple sign mistake will give us a different solution. So this expression is correct. Now we'll arrange in this way. So summation, so some rearrangement has to be done so that you can equate the coefficients, right. That's what we are trying to do. So, summation n running from 0 to infinity n minus 1 a n x to the power n minus 2 plus summation n running from 2 to infinity. This will become 3 n minus 2, but then we have 3 n and minus of 6. So, that this will simply become 3 n minus 3. Then we will have a n minus 2 x to the power n minus 2. So, just to match same n minus 2, we have rearranged this series and we are starting from 2, not from 0, but from 2. So, in order to keep the same number of terms, we are taking, instead of 3 n minus 3, we are 3 n plus 3, we are doing it 3 n minus 3, then n will be replaced by n minus 2. So, basically you are replacing n by n minus 2. So, in a way you are shifting the origin from n to n minus 2, and then remaining terms, I mean rest of the terms will be same. Okay. The reason why we are doing it, because here we have x n minus 2. So, we want to keep the same powers in a way. So, now we will rearrange the term, and this will become summation n running from 2 to infinity. We will have n minus 1 a n plus 3 n minus of 2, 3 n minus of 3 into a n minus 2 plus multiplied by x to the power n minus 2 equals to 0. So, if that means let us go to the, so let me just match. So, n into n into n minus 1 into a n and plus 3 n minus 3 into a n minus 2 into x to the power n minus 2, right. So, when n is 0, then it will vanish, and when n is 1, then also it will vanish, fine. So, we will have this many terms. Okay. Now, let us go to the next page. So, if equation 1, that means or 2 maybe, I am not sure, yeah, 2. So, if equation 2 is a solution of the given equation, then the left hand side must vanish. So, left hand side must vanish means x cannot be 0. So, that means the coefficients multiplied with x n, that those coefficients must be 0, right. So, then each coefficient of this series, then each coefficients of this series in last equation must be 0. In a way, we are saying n into n minus 1 into a n plus 3 n minus 3 into a n minus 2 must be 0 for all n greater or equal to 2, right. So, this is basically a recursive relation or an induction mathematical induction formula. So, what will happen is from here we will get a n equals to minus of 3 by n a n minus 2 for all n equals to 2, 3, 4 and so on. So, from here what will be our a2? a2 will be minus of 3 by 2 a0, then a3 will be minus of 3 by 3 a1, that means minus of a1. Then we have a4 as minus of 3 by 4 a2, then we have a5 as minus of 3 by 5 a2 and so is it a3, sorry, a3 and so on. So, we can calculate all these terms. So, basically the even ones are a2k equals to minus of 3, it is 2 to the power k, 2 into k, 2 into k into a 2k minus 2, and the odd terms are a 2k plus 1 is equals to minus of 3 by 2k plus 1 a 2k minus 1, right. So, here if it is 5, then here it is 3. So, that means you have 2 less. So, basically if it is 2k plus 1, then on the right hand side it will be 2k minus 1. So, that is how we are calculating the terms basically. So, multiplying the corresponding numbers of the first column. So, if we multiply the a2k minus 2, so whatever expression we have here, we can put that. Then similarly, 2k minus 4 can be replaced by 2k minus 6 and so on. So, ultimately, by multiplying the even and odd columns, basically I am calling this as even column and this as a odd column. So, but there is no even and odd column here, but since we have even terms and odd terms, so this is even column, that is odd column. I hope that is clear. So, even and odd columns, then a2k will become minus 1 to the power k 3 to the power k by 2 to the power k into factorial k a0, and similarly we will have a2k plus 1 is equals to minus 1 to the power k 3 to the power k, then divided by 357 dot 2k plus 1 into a1 for all k greater or equal to 1. Right. So, now we have collections of even terms, we have collections of odd terms. So, therefore, the required solution will be, substituting these in the solution y, in the solution 1. So, then our yx is summation n running from 0 to infinity an y to the power n. So, we can separate even and odd terms. So, a0 y to the power 0, then a2 y square dot up to a 2n or 2k plus dot and so on y 2k. Similarly, we can separate the odd terms. So, a1 y1 plus a3 a1 this is x x to the power 0 x square x to the power 2k, this is x1, this is x cube, x to the power 1, then this is x3 dot and so on. So, a0 x to the power 0 is simply a0 and x square is given by, so we've seen that, so here we can summarize this as summation k running from, so a0 plus summation k running from 1 to infinity a 2k x to the power 2k, and here we will have a1 plus summation k running from 1 to infinity a 2k plus 1 into x to the power 2k plus 1, right. So, I will substitute a0 a2k. So, this is a0 plus summation k running from 1 to infinity whatever the term we had, minus 1 to the power k into 3 to the power k divided by 2 to the power k into factorial k into x to the power 2k, and similarly we can take a1 out. So, this will be 1 plus summation k running from 1 to infinity minus 1 to the power k 3 to the power k factorial 2 to the power k factorial k divided by 2k plus 1 factorial and x to the power 2k plus 1, right, something like this. Yes. So, this is actually the series solution, right. So, it as you can see, instead of usually writing the solution as a complementary function or that is getting the auxiliary equation and then writing the complementary function and particular integral, doing the series solution is quite hectic in a way, not hectic, but also it is very lengthy, right, and we have to write find out these recursive relations. From there we determine the coefficients, then you put it back into your equation, and this will be your required solution. Please match this term whether you are getting this factorial relation or not. It may be possible that there might be some error, but this is just algebraic calculation, right. So, whatever term we had here, where is that? So, minus 1 to the power k 3 to the power k a1 divided by 357 2k plus 1. So, that means we are doing 2k plus 1 factorial. So, we are adjusting one 2 to the power k term. So, that means we are looking for the factorial terms, whatever remaining is left, that we have adjusted in the numerator and denominator. So, it becomes 2k plus 1 factorial. Yes. So, this is the series solution when we have a regular point, right, and as you can see, it is still very lengthy. Now, we will work on one example where we have the singular point. So, this is for ordinary point. We will look for one example, or we will solve one example where we have singular point. So, let us consider this example, example 2. So, solve as usual, solve x square d square y by dx square minus of x dy dx plus x square plus 1 into y equals to 0. This is equation number 1. So, the solution goes like this. Solve this near its singularity, near the singularity x equals to 0, near the singularity x equals to 0. So, the point, obviously the point x equals to 0 is the regular singular point, because if you divide by x square, then capital Px will have 1 by x and the maximum power is 1. So, therefore, it is a regular singular point of the equation 1, Now, for the solution, let us take y x equals to x to the power rho c0 plus c1x plus c2x square dotted up to cn xn, an or cn does not matter. So, this is basically summation n running from 0 to infinity x to the power rho plus n into cn, right. Let us call it as equation number 2. So, from here we will get dy dx as summation n running from 0 to infinity rho plus n, sorry, there is an x to the power rho plus n cn into x to the power rho plus n minus 1, and d square y by dx square as summation n running from 0 to infinity rho plus n minus 1 cn x to the power rho plus n minus 2. This is equation number 3. Now, let us put everything back. So, if we put everything back in equation 1, then from equation 1, what do we get? We will get summation. So, just like previous example, summation n running from 0 to infinity cn rho plus n minus 1 x to the power rho plus n minus 2 into x square. So, x square. So, this will become simply x square, let us write, it does not hurt. So, summation n running from 0 to infinity, we will have rho plus n cn x to the power rho plus n minus 1, put x here, and plus x square plus 1, we will have y. So, y is summation n running from 0 to infinity x to the power rho plus n cn equals to 0, right. So, now from here this x plus x to the power rho plus n minus of 2 plus 2. So, that will simply become x to the power rho plus n. Here it will become x to the power rho plus n minus 1 plus 1. So, that will give x to the power rho plus n, and that will remain as it is. So, what will happen is we will have this expression, that is summation n running from 0 to infinity. This is a relatively lengthy calculation, rho plus n minus 1 x to the power rho plus n minus summation n running from 0 to infinity rho plus n cn x to the power rho plus n plus summation n running from 0 to infinity x to the power rho plus n cn plus summation n running from 0 to infinity Cn x to the power rho plus n plus 2. We have broken down this term. So, these many terms we will have equal to 0. Now, corresponding to n equals to 0, corresponding to n equal, let us go to the next page. We can call this as equation number 3. Let us call it as equation number 4. Okay. Okay. Now, corresponding to n equals to n equals to 0, the coefficient of the lower degree term, i.e. that is x to the power rho is C0 rho minus 1 minus of C0 rho plus C0 equals to C0 rho minus 1 whole square, right. So, C0 is out, C0 minus rho whole square. This is the coefficient of x to the power rho when n equals to 0, and hence there is something called the indicial equation is C0 into rho minus 1 whole square, and therefore, we will come back to this. What does this indicial equation mean? So, therefore, we will have rho equals to 1 and rho equals to 1 since C0 is non-zero, the coefficient is non-zero. Thus, the roots of the indicial equation are equal. Then putting the coefficients of x to the power rho plus 1 equal to 0, we get C1 rho plus 1 into rho minus C1 rho plus 1 plus C1 equals to 0. So, this gives C1 equals to 0, because if we put rho equals to 1, so then in that case we will have C1 as 0, right. So, basically it will give C1 equals to 0. Now, putting the coefficients of x to the power rho plus n equal to 0, we get Cn rho plus n into rho plus n minus 1 minus of Cn rho plus n plus Cn minus 2 plus Cn equals to 0. So, from here we will get Cn equals to minus of Cn minus 2 by rho plus n minus 1 whole square. What is this indicial equation? We will explain in the next class. So, this actually comes from the Frobenius solution. So, but whenever we are given this singular solution, so from there we just equate the coefficient of n0, we extract the coefficient of n0, from there you just make that coefficient equals to coefficient of n0 n equals to 0 as equals to 0, assuming that C0 is non-zero, and from there we will get the two values of rho. Using that we will find the C1. So, for n equals to 0 and n equals to 1, those two terms are taken care of. Now, the remaining infinite series can start from n equals to 2, and then in order this y x equals to x to the power rho plus n into Cn summation n from 0 to infinity is a solution, then rest of the coefficient of that series must vanish, right. So, if it must vanish, then this is the required relation. So, here n is Cn is minus of Cn minus 2 by rho plus n minus of 1 whole square. So, from here basically our n is greater or equal to 2. So, we can get C2 equals to minus of C0 rho plus n minus 1 whole square. So, n is 0. So, this is basically minus of C0 rho minus 1 whole square, Similarly, we'll have C3 as rho n plus 1. So, if n is, similarly, if we have C3, so C3 will become minus of C1, and we are substituting n equals to 3. When we are substituting n equals to 2, this is becoming rho plus 1, sorry, this will become rho plus 2 whole square, and so on. So, we can calculate the remaining coefficient. So, now putting the values of C1, C2, C3 in the solution y, what do we get? We get yx equals to C0 x to the power rho, C0 x to the power rho 1 minus x square by rho plus 1 whole square plus x to the power 4 rho plus 1 whole square, rho plus 3 whole square minus dot dot and so on. And this can be, so this is x to the power rho, and this can be thought of as C0 w. Let us say some function of x. So, this entire thing we are calling it as wx. So, again, if we substitute yx equals to C0 wx in our original equation, then this will turn out to be x square d square wx by dx square minus of x dw by dx plus x square plus 1 into w equals to rho minus 1 whole square x to the power rho. This is what we will get if we substitute y is equals to this. And from here, thus we see that the equation is satisfied as by w as well, by w as well as by w as well as dw by d rho, right. So, if rho is 1, so now we can calculate w at rho equals to 1, which is given by x into 1 minus x square by 2 square plus x to the power 4 by 2 square times 4 square dot dot and so on, which is equals to w1. So, basically we have dw by d rho equals to x to the power rho log of x 1 minus x square by rho plus 1 whole square plus x to the power 4 by rho plus 1 whole square, rho plus 3 whole square, and minus dot dot and so on, plus x to the power rho 2x square by rho plus 1 whole square, and similarly we can compute the remaining terms. So, this dw by d rho at rho is equals to 1 is w1 log of x plus x into x square by 2 square minus x to the power 4 by 2 to the 2 square 4 square into 1 plus 1 by 2 minus dot dot and so on. So, this is our w2 say. So, therefore, the required general solution, is y is equals to a w1 plus b w2, where a w1 will be this entire expression which we calculated in the previous page, and then b into w2 is whatever we have calculated here, where a and b are arbitrary constants. So, because of time constraint, I derived the solution, but in the next class I will tell you how do we calculate this indicial equation and why are we introducing this w1 and w2, right. But the general idea is to write down, when you have a singular point, when you have a singular point, you write down the solution as yx equals to x to the power rho into summation n from 0 to infinity an or cn x to the power n, and from there we put everything back into the original equation. But since you already have x to the power n terms, there will be some extra terms, and those extra terms will be equated to 0. From there we will obtain the values of rho, and then we use those values of rho to get the remaining cn's or an's, whatever, and then you again put it back, and from there we calculate these w1 and w2, with the help of which we write down the general solution, right? So this is a technique or a series solution to calculate the solution of an ordinary differential equation which has singular points, right? So I'll stop here today. We'll continue this discussion tomorrow, and I will start with the same example, and I'll tell you about this indicial equation and this wi's, and then we'll conclude this example, and then we'll move on to our special function part. So thank you for your attention, and I'll see you in the next class.